Hello, Physics 20s. Mr. Jukley here again. Today we're going to go through Unit 6, Lesson 7. We're actually, through this weird corona time that we're in, only going to go through part of this lesson. We're going to go through the part about resonance and the part about standing waves, but we're going to kind of skip over stringed instruments, which is kind of unfortunate because the music side of this is one of, well, it's a lot of people's favorite part. It's just not necessarily needed for the next level. It's not needed for Physics 30. So for the sake of, you know, essentials, I guess, we're only looking at the first little section. It's still neat stuff, though, so still definitely worth checking out. So resonance is when we have a regular repeating force, so in other words, a periodic force that is applied in phase with the natural frequency that something likes to resonate at. And it turns out that just about everything has a natural resonating frequency, at least one, I should say, natural resonating frequency. So remember, frequency is how often it cycles or how many times it cycles per second. Cool. So when we're thinking about all these kids over here, these pendulums that are back here, you know that they swing back and forth with a very, very, very particular frequency, kind of like we're showing here. So swinging back and forth and back and forth. Maybe that looked like maybe one cycle per second. So if a person is pushing as they're moving forward and they're pushing forward and then letting them go backwards, and every single time with the frequency that that kid on the swing is resonating with, they're going to go higher and higher and higher and higher. And if the force is again in phase, we're going to increase the amplitude of the oscillation or increase the amplitude of the vibration. So I can't really show you this with a pendulum, at least not easily. Remember how the springs work out last couple videos that I made for you, not super hot. But what I've got for you is I've got a couple of videos that other people have made that are way better at making videos than I am. So videos I want you to check out here. So there's a whole bunch of different things. One of the ideas is materials can resonate so much that it leads to damage. So like airplanes and stuff like that with the propeller spinning around with particular frequencies, they can rattle bolts loose. Bridges, one that I don't have up here is something called Tacoma Narrows. Tacoma Narrows. Just look up the bridge claps from that and you can kind of see it a little bit. But the videos that I chose for you here are all about breaking wine glasses for the most part. So there's 3 videos. There's this wine glass resonance in slow motion by Marty33. This one has the best animation to show you the actual wine glass side of things. So I really like that one for this. This one, Physics Girl, which by the way is an awesome YouTube personality or channel or whatever if you want to call it. I mean, she's a person obviously, but her channel is an awesome thing if you want to look at some physics stuff in a very entertaining way. So how I broke a wine glass with a voice. I think this one is best for showing resonance because she uses other examples for resonance, which is really, really nice. And then this middle one here, this one is just plain old funny. Like this kid is, that kid makes me smile, that kid makes me laugh. Chase Chocolate is the YouTube personality or channel or whatever you want to look at for that one. So I would recommend watching at least, well, you know what? All 3 of them are awesome, and all 3 of them are entertaining enough that I'll just say watch all 3 of them. Check those out. So you might want to put the video on pause right now and go for that. One activity, so if you've paused it and you're back, that's great. If you haven't paused it, you might want to pause it and check those out. One activity is we live in a winter climate that there can be lots and lots and lots and lots of snow, lots of mud, stuff like that. I have been stuck in my vehicle a handful of times. I have helped people, push people out even more. Even just last winter, I think 4 or 5 people probably helped push out of holes and ruts and stuff in their vehicles. For those of you who are taking driver's education or even have been stuck, how do you get unstuck? Right? So you can increase traction. That's one way. Sometimes that helps, that doesn't. you know, you can floor it and mud flies up everywhere like you kind of see right here. That actually doesn't help, it just digs you deeper. The best way is to push with resonance, right? So you push it forward a little bit, let it roll back. Then as it's about to roll forward, you push it forward a little bit more, goes a little bit further, let it roll back a little bit further, then you push it forward a little bit further. So every time it's moving forward, every time it goes back to its maximum, you push it forward as far as you can. And that forward and backwards gradually get bigger and bigger and bigger until you get out of the rut and you can drive off. Hopefully that made sense the way I explained it there. This one's actually an animation that I want to show people. So essentially what we look at with these standing waves, I'll kind of show you as we go through. So you remember when I sent a wave and it hit a fixed end, so a wave pulse and it hit a fixed end, we kind of talked about this. The wave's going this way, hits a fixed end, it actually comes back inverted. We talked about that, we mentioned it, and then we kind of said, okay, well, we won't deal with that very much. But it comes back inverted. But what happens if I continually send waves, so crests and troughs, and they hit that fixed end, and then they reflect backwards? But if they reflect backwards, that's a terrible drawing of this. If they reflect backwards so that they're in phase, so as this trough, let's color code it a little bit here, as this trough is coming back, there's another trough that's coming the other way. So one trough is going this way, the other one is going this way. I guess that's technically a crest, but the waves are perfectly in phase. So trough with trough, or trough is always meeting trough, and crest is always meeting crest. That sounds an awful lot like constructive interference. So let's look at the actual animation here before we go much further. So here's a wonderful animation. The blue line is the wave that is moving towards the right. The green line is the wave that is moving, the reflected wave that is moving towards the left, and the black wave is the overall wave. One thing I should mention with this, the stuff along the bottom is technically incorrect. We'll fix that in a second, the ends and ANs, and we'll talk about what they mean. Oh no, maybe it's not. Maybe it's something else I'm thinking of. No, okay, so those are fine. I had a closer look at it now. Never mind. My bad. But anyways, what we see with this, as we're going through it and as we look at this sort of pattern that's being formed, remembering the black line is the resultant, right, or the addition of the two waves, the green moving towards the left, the blue moving towards the right, at points that we see right here, right here, right here, and right here, does it ever actually move off the equilibrium position on those red spots? It doesn't. So it's always, no matter what is there, it's always got zero amplitude. That is destructive interference, especially when we pause it right. Wait for it. Now. I can't actually pause it, but now. You can see I've got a green crest, a blue trough, or vice versa, and it completely cancels out. Whereas, let's erase those red dots, and I'm just going to shift them over by a little bit. So I'm going to replace the red dots right here, and right here. And now we've got a place where we continually have crest with crest and trough with trough. So we get constructive interference. The black line is bigger, and it's actually the sum of the blue and the green line. So constructive interference and continual constructive interference at some spots, and continual destructive interference at others. Okay, I got to walk over to the computer and put this out so I can actually write on it a little bit here. Very nice animation though. Yeah, let's get rid of those. That's fine. Where's the thing I'm looking for? There's, oh boy. Oh boy. Okay, so end up with that. The terms that we need to know for this, and the terms that we need to be familiar with this, is where we have complete destructive interference, we're going to call nodes. So nodes is where we have continual destructive interference and never actually leaves the equilibrium position, whereas antinodes, so there and there, are we have continual constructive interference over and over and over again. It's continually switching from crest to trough, and they're doing that at the same time. So we kind of already did this question. Here's a question for you, another question for you, highlighted in blue here. The distance from node to node in terms of wavelength. So let's go back here, let's clean this up a little bit, tiny bit. The distance from node to node in terms of wavelength. Use red for this one. So if I'm starting with my first node at the fixed end, And then I go to my second node right there. How much of a wavelength is that? Well, it's only half of a wavelength, right? If I draw the full wavelength, that's actually in between 3 or that many or whatever, so that's 2 wavelengths in red. But from node to node, if I just look at this, it's half of a wavelength. Now, of course, we also have the reflected wave here, so I'm going to highlight the reflected wave in dotted green. So there's my reflected wave, and still, even when I think about this, it's half of a wavelength for red or half of a wavelength for green from node to node. Cool. So some things that you can check out with this, and I've got some great ideas for this as well. If anybody's thinking about opening up a restaurant, you know how, when you're waiting in the restaurant, you often have music and you often have a fireplace, especially in winter. Why not combine the two? Amazing. Why not combine the two? So the first video here by Veritasium is a musical fire table. It's a fireplace that plays along to the music. This one, the 2D stuff that they got going, it's okay, but they have amazing animations for 1D. So check out the 1D animations for this first one. And then the second one, this is what I picture at a restaurant. So Jay's Place. Maybe that's the name for the restaurant. I don't know. But you walk in the door and then there's the little fireplace. Fire should be red. Yeah, that's nice. But the fire is playing along to the music. So check out both of those and see what I mean. It's another cool application of these standing waves and of resonance. Last sort of example that we're going to look at is for baseball players out there or people who have played slow pitch or anything like that. You know that there's a sweet spot, and in most sports there's a sweet spot on your stick, your racket, your bat, whatever it is that you're hitting stuff with. When you hit that sweet spot, you're actually hitting a node, so a place where your bat does not like to vibrate. If it does not like to vibrate, the energy is not going to transfer into the bat is not going to vibrate, and the ball's going to go an awful lot further. But if you hit it too close to the handle, oh boy, does that ever hurt, because the bat starts to vibrate. You've hit it at an antinode or a natural antinode for that bat. The bat starts to vibrate, loses a ton of energy. The ball doesn't go very far because its energy is now transferred into the bat. And remember, this is where you're hanging on. So what happens to your hands? There's a big meaty hand with some fingers and stuff. You know how good I am at drawing. It starts to vibrate like crazy, and that's why it hurts your hands. Cool. Okay. Last thing that I'll kind of mention for this, the rest of this lesson is about stringed instruments. Again, unfortunately, for the COVID out of time sort of stuff that we've got, we're not going to look at that as a class in any kind of detail. Remember, you are totally welcome to go through and check it out. If you're interested in it, by all means, go through and check it out. But as a class, we're not going to do that. And if you're checking out, feel free to ask questions and stuff. Anyways, that is it for today. Physics 20s. Let's get rid of that frowny face. Another good lesson. That's it for today, Physics 20s. We will, or for this lesson, I should say. We'll talk to you again soon. Bye for now.